Welcome to qnawire.
So we're going to, my apologies, we're going to apply Newton's second to Newton's second, the Gauss's law, my apologies, to the spherical Gaussian surface with radius r. We're going to calculate then the electric field at the surface of the Gaussian sphere. So here, for part A, we can say that for part A, part I, r is less than A, and we can then say that the electric field is going to be equaling the magnitude of the electric field times the area, and here we have E times 4 pi r squared. We know that the charged enclosed is equaling 0 because there isn't any charged enclosed, and so we can then say that here the electric flux would be equaling, according to Gauss's law, the enclosed charge divided by epsilon naught, or the permittivity of free space. And so this is, we know that this is equaling 0, so the electric field is equaling 0 as well. For part A, part 2, we know that if A is less than R and less than B, this lies within the conductor. And so at this point region are, because lie within the conductor of the small shell, again, the electric field is equaling 0. For part 3, essentially, we have this sphere, and now we can say that here, B less than R less than C, and here we can apply Gauss's law. Here, again, the electric field is equaling the magnitude of the magnetic flux, rather, is equal to the magnitude of the electric field multiplied by the area. This is equaling E times 4 pi r squared. Here, the sphere encloses all small shell and none of the large shell. So here, the enclosed charge is equaling plus 2 times q. The magnetic flux would then be equaling the enclosed charge divided by the epsilon naught. And this is giving us E times 4 pi r squared equaling 2q over epsilon naught. And so the electric field here is equaling 2q over 4 pi epsilon naught r squared. Here, because the enclosed charge is positive, the electric field would be radially outward. And so, finally, for part 4, we have that C less than R less than D, and here, points. This is the diagram for part V. However, for part 4, C less than R less than D, this is again within the conductor. So the electric field is equaling 0. And then for part 5, which is drawn here, that R is greater than D, and so this encloses the shell and all of the large shell. So here the enclosed charge is equaling plus 2q plus 4q. This is equaling 6q. And the electric flux is again equaling the magnitude of the electric field times the surface area. E is equaling E. This is equaling E times 4 pi r squared. And so we can then, by Gauss's law, find that the electric field is equaling 6 times q divided by 4 pi epsilon naught times r squared. Because the enclosed charge, rather, is positive, this is again radially outward. And then if you wanted to essentially graph all of these, this is what the graph would look like the electric field versus R. This would be our final graph. The end of the solution. Thank you for watching.